All right, we're back. We're on page 142 of math analysis. We've been talking about trig form of complex numbers. We can multiply, divide, raise to powers. And what we're going to find out here is we can take nth roots. One thing that trig form is really not meant for is adding and subtracting complex numbers. It just doesn't work very well. Rectangular or standard or a plus bi form is way better for that. So let's take a look at this next thing that we can do. And this is like a little eye-opening or kind of weird, I guess. So this fact is important. So it is that every complex number has exactly n nth roots. So you have 7 7th roots, you have 12 12th roots, you have 55 55th roots. That was a hard one. And so what that means is that if you have a number, right, and you raise it to the, so say you're talking about the 10 10th roots, right? Each of the 10th roots, if you raise them to the 10th power, will give you the original number. So a number is an nth root. So z sub k here is an nth root of another number z if z sub k to the n is equal to z. So this can be a weird, it's like a weird thing when you first encounter it, right? So here I've given you the 4 4th roots of radical 3 over 2 minus 1/2 I. So I've given you the 4 4th roots. We want to show that they're the 4th roots. So to do that, what I'm going to do is raise them to the 4th power. So if I do z1 to the 4th, that's going to be this negative 4 pi over 24, so negative pi over 6. And then the cosine of negative pi over 6 is the same as cosine of 11 pi over 6. So we get this cosine and sine. So z2 to the 4th. Is that a 2? I don't think so. I mean, it's meant to be. z2 is going to give me cis 11 pi over 6. I mean, these angles right now, these are coterminal. And so we know that it's got to give you the same thing. So it's going to give you radical 3 over 2 minus 1/2 I. Look at that. Those are two different things. Like 11 pi over 24 and negative pi over 24 are not coterminal angles. These are two different things. 23 pi over 4, also not coterminal. So if I do z3 to the 4th, that'll be cis. So this is 23 pi over 6. So 23 pi over 6, 2 pi is 12 pi over 6. So if I subtract that twice, I would get negative pi over 6. So cis negative pi, negative pi over 6, yeah. Negative pi over 6, which is, again, we already did that one. That was z1. So this will give me radical 3 over 2 minus 1/2 I. So this, I don't know, maybe this is like a weird result to you. Maybe it's not. Maybe you're like, yeah, obviously. I don't know how you could think that, but maybe. This will give me. But every complex number has n nth roots. So what's this one? 36. So I'm thinking 2 pi would be 12 pi over 6. So 3 of those is 36 pi over 36. 36 pi over, no, 36 pi over 6. Then subtract it off and you get negative pi over 6 again. So we're back down to negative pi over 6. So all of these raised to the 4th power give us, so these are all, basically all of those ended up coterminal. All of these to the 4th power gave us the same thing. They are the 4 4th roots of radical 3 over 2 minus 1/2 I. So that's kind of interesting. Another sort of interesting thing, I'm not going to be able to draw it for these, but they all differ by the same amount. So for example, here, from here to here is pi over 2, right? If I add, so what's pi over 2 and 20? So 12. If I add 12 pi over 24, I get that. If I add it again, I get that. If I add it again, I get that. And then why are there only, oh yeah, because I only have to add it 3 times because there are 4 of them. So they're also evenly distributed, right? They're all pi over 2 apart. That's kind of interesting. And we're going to end up using that actually a lot. So they're evenly distributed around basically the unit circle. or a circle of a certain radius, so a circle, and they are, I don't know, let's just do it. So we're gonna use Euler's formula to work out like how to find these, right? So we've shown that they are the 4 fourth roots. How would I go about finding them? Well, first, what we're gonna do is we're gonna look at this and we're gonna say, here's our complex number, r cis theta. So we wanna find an expression for all angles coterminal to theta, and we're gonna use k instead of n because it's the nth roots, so it's getting used already. So we're just gonna say k. So I'm gonna say, we could do theta plus 2 pi k, where k is an element of the integers, right? So these are all of the angles that are coterminal to theta. Just keep adding 2 pi. So that means that z can really be thought of as r cis theta plus 2 pi k, where k is an element. It's going to get real annoying writing that over and over. So then we can use Euler's formula on that. R e to the I theta plus 2 pi k, where k is an element of the integers. Okay, so far so good. Now what we're going to do is just raise everything to the 1 over n power, right? That's how you take an nth root. So that's what we're going to do. So we're going to say z to the 1 over n. So remember, r is the absolute value of the complex number. R is a real number. So we can find the nth root of a real number the way that we've always done that. So it's going to be r to the 1 over n. And then e to the, how to write this? I guess I'll write it as just I theta plus 2 pi k all over n, where k is an element of the integers, and then n is going to be the nth root. So if you're finding the cube roots, n is 3. If you're finding the 12th roots, n is 12, and so on. Well, I don't know if it's a better way. So I'm just going to rewrite this. So z to the 1 over n is r to the 1 over n, and then cis, I'm going to write it as, how should I write it? So I'm going to write it as theta plus 2 pi k over n, where k is an element of the integers. But like, it's convenient, like really convenient, to think of this also as theta over n plus 2 pi over n times k. Like that's another very convenient way, and that's why they're arrayed. That's why they're evenly distributed around a unit circle, because if n is 3, then you're doing 2 pi over 3, and then you just count by k, and you'll have 2 pi over 3 in between them every time. So however you want to do that. So I'm going to keep going for a little bit before we actually do something, or before I cut this, I guess, because there's just 2 more steps basically. So k is, n is fixed rather. K can change. K is an element of the integers, but it can change. So let's see what we're going to do. So we're saying that we have theta over n plus 2 pi k over n, right? Where k is an element of the integers. So these are our arguments. So if I say, like, let's say that k is equal to 1, right? If k is equal to 1, well, k is equal to 0. If k is 0, then I just get theta divided by n. If k is 1, I get theta divided by n plus 2 pi over n, because k is equal to 1. If k is 2, I'm going to get theta over n plus 2 pi over n times 2. And I can just keep going, right? And eventually, I'm going to get to, so dot, 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 dot. I'm going to get to k is equal to, let's say, n minus 2, right? That's going to give me theta over n plus 2 pi over n times n minus 1, n minus 2. All right, we're getting closer. K is n minus 1. Theta over n plus 2 pi over n. Oh my God, my n's have become 2's. N, and then n minus 1. Nothing that I've written so far has been coterminal to anything else that I've written. The reason for that is that So n is bigger than k. I guess I should probably have said that, but whatever. N is bigger than k. If n is bigger than k, it takes a while for that to catch up. If n is bigger than k, then I'm like, this is less than 1, so it's not a full revolution. This is less than a full revolution. This is not a full revolution yet. This is not a full revolution. If k is equal to n, then I'll get theta over n plus 2 pi over n times n, which is theta over n plus 2 pi. This and this are coterminal. So that's not a new unique representation. So we should stop before we get there. So we should stop here. So what we're going to do is we're going to let k go from 0 up to n minus 1. So if you're finding the 8th roots, you're going to go from 0 to 7. If you're finding the 53rd roots, you go from 0 to 52. And the reason you want to stop is that you don't want to just like duplicate a representation of the same thing, right? So polar representation, not unique. There's more than one way to refer to a particular value. Rectangular is unique. So this, and this will give you the same rectangular representation. So they're the same. So we stop. And so overall, all the easier said than done. All of it's easier to, no, sorry, it's the opposite of that. All of this is easier done than said. So I'm gonna say cis, let's say theta over n plus 2 pi over n times k, where k goes from 0 to n minus 1. If we do that, we will get all of our nth roots. And so I'm going to stop the video here. This is a big deal. Stop it here. I'll come back in the next one and we will do some examples because you really got to use it to like know what's happening. But anyway, be back in the next one and we will keep going. So I'll see you there.